Okay, so in this video, let's talk about the photochemistry of carbonyl compound. So I hope now the term chromophore is a general term for you. Like normally, what the chromophore means is that when you take a molecule like this, let's say this is a molecule. So the chromophore is the part where the excitation happens. Otherwise, the light is being absorbed. So in this case, this is the part where the excitation would happen. So we call this particular part as the chromophore of the molecule. Now, in our previous videos, we have talked about this chromophore and we have talked about the effect of this chromophore to a general reaction. I hope you know these basic terms. Like if you want to watch that video and gain the knowledge, I will put the link here so you can go there and memorize your what we have talked about for the chromophores, right? Now we are going to talk about the carbonyl compounds and the photochemical reactions of these carbonyl compounds. When we talk about the carbonyl compounds, first thing what you need to know is we are going to look at this chromophore. We have this carbon double bonded oxygen as our chromophore. So there is the N to pi star transition. This is the excitation process. N to pi star transitions. There are electrons in the oxygen which is non-bonded, so they are going to excited into the pi star orbitals. Now when we look at the reactions, right, there can be two types of reactions. Now let's take this molecule like this. So there can be either this kind of cleavage, like when we talk about the cleavages, like otherwise the reactions, most of the time we are going to talk about bond breaking and bond forming. So either this can happen through like this. So let's say we have obtained this reactant with this type of molecule, right? So this X may be halogen, right? Chlorine, benzene, chlorine, bromine likewise. When these two react with radical manner, radical formation or a radical reaction, we can obtain this kind of intermediates. So this is basically radically cleaved. This pi bond over here, it will cleaved also. This one electron will come and bonded with another one of these guys. So let me draw it properly. So here we have this cleavage, okay, and the other electron is going here. So that's why we have the radical of X and we have the radical of this one. So after this process, there can be this X can be joined with our original molecule, or these another two molecules can join together. The reaction can continue go on. Now this is a one type of reaction. As you can see, the reaction involves in the cleavage of carbon oxygen pi bond, right? Carbon oxygen pi bond. Now let's say you have a weak bond, right? Let's take this A. Now you have a weak bond closer to your chromophore. So this is your chromophore, right? This is your chromophore. This is your weak bond. Now if you have a weak bond closer to chromophore, there's a tendency to this bond to be broken. Now when you do the cleavage, right, otherwise when you introduce the light, excitation would happen in this chromophore that will result in breaking on this bond. So you will have two bonds like this. Like this. Okay, this can also be happen. This will happen when you have a weak bond, right? That's the important part. This will happen when you have a weak bond. So when we do the examples and when we do the problems, you will see exactly how we can choose between these two reactions. Now we call these reactions as homolytic cleavages. Homolytic cleavage reaction. So this is the first one and this is the second one. Now we have another problem, right? So let's say we have a molecule like this. Okay, now how can we guess the reaction mechanism? Like, otherwise, how can we guess the transition? Now you can see when we look at the chromophores, there are two chromophores, right? This carbonyl group, and also there's a pi bond. You know the pi bond is also a chromophore, right? So if I ask you what are the possible transitions, there are two possible transitions. First thing is the normal n to pi star transition, right? N to pi star transitions, which is occurring at carbonyl group or otherwise in the oxygen, and there is also pi to pi star transition. Pi to pi star transition, which is occurring at this pi bond. Okay, now when you have these two types of chromophores in the same molecule, right, what you need to look at is the delocalization. So you need to look at the delocalization. This is the important thing, delocalization. If you have higher delocalization, right, if your molecule has higher delocalization, as an example, if I introduce a benzene ring to our molecule, now here you have a benzene ring. Now again, if I ask you what are the chromophores, there are two types of chromophores, right? Here we have one chromophore and here we have another chromophore. What are the possible transitions? There are two types of transitions, n to pi star occurring from this oxygen and carbon, and also pi to pi star occurring at the benzene ring. Now in this case you can see that benzene ring provides delocalization to the structure, and I hope you know from our basic organic chemistry that delocalization is resulting in the stabilization of the molecule. Stabilization. Okay, the delocalization will result in stabilization of a molecule. Now when you have this stabilization, right, when you have this stabilization, you will see that that particular transition. So if I explain to you that based on this example, right, there are two transitions can happen, n to pi star and pi to pi star, but here you have the delocalization. So this pi to pi star transition, right, this one is stabilized because of the delocalization. Now what happens when stabilization happens? So if I explain to you based on the energy diagrams, here look at this one. The electron is there. When the excitation is going to happen, electron will jump into the higher excited state. Now if your excited state is unstabilized, right, it's not stabilized, it's not stable, it has higher energy, which means it's not stable, right? So this electron doesn't like to be in here, right? It would try its best to come back into the ground state and get stabilized. So the lifetime in this excited state at the unstable process is shorter. Why? The excited electron doesn't like to be there. It will try its best to come back. So it will quickly come back into the ground state due to the instability. So you have a low lifetime. If you are looking at a reaction, right, if you look at the reaction mechanism, there must be a certain time in order to collide the reactants, to go through the reactions, right? Let's say as an example, you need 1 second, right? You need to 1 second in order to go through with the reaction, right? But let's say your excited state only occurred at only half a second. So it's not enough time to go through with the reaction. The reaction won't happen at that case. So when you have low lifetime, right? When you have low lifetime, that particular excited state doesn't provide for your reaction because there is not enough time for the reaction. So when you have these two types of transitions, right, one is getting more stabilized, it will have higher lifetime. So reaction would much more feasible on that particular pathway because it has more time to react on that transition. So when you have this delocalization, it will result in the stabilization of the molecule. Now with the stabilization of the molecule, you will have much more higher lifespan transitions, or otherwise excited states. That's why when you have higher delocalization, you will choose pi to pi star transition as the main transition. Otherwise, you go through the reaction mechanism with the pi to pi star transition when you have higher delocalization. But when you have lower delocalization, like this, here you have lower delocalization. In this case, otherwise 2 pi bonds are there. It is also considered as low delocalization. These cases we can ignore the pi to pi star transition. We can continue with the n to pi star transition, right? So when you have higher delocalization, otherwise more pi bonds than 2, maybe 3 pi bonds, 4 pi bonds, benzene rings, 2 benzene rings, then you need to choose pi to pi star transition as the main transition, otherwise the reactions main transition. If you have lower delocalization, otherwise lower pi bonds like this 1 or 2, then you will go with the n to pi star transition. Okay, I hope you get the idea. Why do we use this? Why do we choose pi to pi star transition or n to pi star transition? It's based on the delocalization. When you have the higher delocalization, your molecule will be stabilized. So the pi to pi star transition, which is stabilized by the delocalization, prefers to join with the reaction. Otherwise, prefer to react with the reactants. How can I say? Prefer to involve with the reaction mechanism much more efficiently than the other one, because it's stabilized. It has a higher lifetime. It has more time to react than the other. Okay, I hope you get the idea about it. So this is the case. So when you have low delocalization, otherwise low number of pi bonds, you will go with n to pi transitions. If you have higher pi bonds, otherwise higher delocalization with several benzene rings, more pi bonds like this, you go with pi to pi star transition as the main transition mechanism. And then finally, let me talk to you about the two excited states, right? So there are S1 excited state and the T1 excited state. So we have talked about more detailed manner about this excited state, how these are occurring, what are the reasons for each of these excited state differences, right? So I highly recommend you to go back to our playlist and watch that video. I guess it's 4th video, right? So there's a small thing I want to remember you again, which is that T1 excited state has longer lifetime. If your question asks why is that, right? Otherwise, if your question asks this kind of one, let's say there's a molecule A. This molecule A has AS1 excited state and a T1 excited state. So your question states that the reaction would more feasible, otherwise reaction would have more proportion of going through T1 state rather than the S1 state. So you have to explain why is that. So the base of this answer is this one. T1 state has longer lifetime. So if you remember our basic explanation of this excited state. So here we have the ground state. When the excitation happens, it's always S0 to S1, right? So T1 state, otherwise the triplet energy state, is positioned around this. So it has lower energy compared to S1 state. Now the intersystem crossing can happen S1 to T1, right? S1 to T1. So when this happens, so when T1 is occupied, okay, when T1 is occupied, the relaxation from T1 to S0, T1 to S0 is very low. This is very low because transition from T1 to S0, this is spin forbidden. If you remember, this is spin forbidden. That's why direct excitation from S0 to T1 doesn't happen. These are spin forbidden transitions. So when you have occupied T1 transitions, like otherwise when you have T1 excited state, that molecule has relatively higher lifetime or longer lifetime in the T1 state compared to S1, because it doesn't have anywhere to go for the relaxation. this is spin forbidden. So this relaxation process is very low. It would take time to relax from T1 to S0. But when you have S1 excited state, right? When you have S1 or singlet excited state, it will come down to the ground state, or S1 to S0 relaxation. This is more prominent. This is more efficient. Why? This is spin allowed. This is spin allowed. This is spin forbidden. So this process takes time. So when they take more and more time, reaction has enough time to interact with this one and go through the mechanism. When you have the singlet excited state, it's spin allowed. So there's a efficient relaxation from S1 to S0. So there are no enough time for the reaction to happen. It will quickly go back into the ground state without involving the reaction. But when you have the T1 state, it will have time. It will take some time in the excited state. So in that time, the reaction will proceed because it would have enough time to go through with that mechanism. That's the key concept. I hope you understand it. So main point is T1 state, or otherwise the triplet excited state. Triplet excited state has longer lifetime compared to singlet excited state, right? Why is that? It's because of the spin forbidden nature of the relaxation from T1 to S0. I hope you understand that. So we have talked a little bit more advanced topics in this particular video. So we will continue into the depth of this photochemistry. I hope you are with me. I will put the link here. You can go to our playlist to get more ideas and more basics of it. So in here, this one also, we have talked about more in-depth review, or otherwise in-depth explanation about this singlet excited state and the triplet excited state in our early video. So you can, if you watch those videos, you will get the clear understanding about how these excited states are forming, why these are getting two different energy values, likewise. So in our next video, we will continue our discussion with the alpha cleavage and the more reactions of the carbonyl compounds. I hope you understand for now. If you have any problems, please feel free to comment below. I will try my best to explain those answers.